Okay, so, do you hear me? Okay. Okay, so now that you've heard about the history of Lean, let's focus on the practice of formalizing mathematics in Lean with Bhavik Mehta from Imperial College in London. Please.
Thank you very much. And thank you very much for having me in this beautiful city. So yes, I will be talking about a practical introduction to formalizing maths in Lean for the working mathematician. The aim of what I will be talking about today is not for the experts in the room, because you will know all this stuff already. I am sorry to all you all. I respect all of the experts in the room, and so you have my full permission to sit on your laptop and do what you feel like. This talk is for the people who don't know much Lean, so that you get the most that is possible out of the rest of the week. And the other caveat I should give at this point is, because the purpose of what I'm going to be talking about today is pedagogical, I will simplify certain things for the sake of making a clearer explanation. Again, I'm sorry to the experts. When I'm lying, I know that I'm lying, and trust me about that. So what will I actually talk about? The first thing I'll talk about is how to read statements. When you see something written in Lean, how can we understand what this is? Talk about the syntax of this and the practice of how to read something like this in practice. Then I'll talk about a proof. I want to talk about roughly what it looks like to understand a proof. If you see a Lean proof, I want to give you the tools you need to step through it and see what this proof is doing. And finally, I want to talk a little bit about writing and reading definitions and statements, and why it's so important to get this right. The stuff I'm going to be talking about is adapted from the work of these excellent people, and amongst other people, but in particular, I borrowed stuff from these folks. Okay, so the first thing I want to talk about is reading statements. When something has been proved in Lean, there will be the statement of the thing and then the proof of the thing. And in order to understand what's happening, we should make sure we understand the statement, make sure we can read it and understand what it's saying. So let's go from the beginning. Lean uses types. It's a type theoretic system. It's a type theory language. What that means is that we will use types instead of sets as Lean's foundational way of saying a collection of stuff. In set theory, naive set theory, or ZFC, the set is the fundamental object, whereas in a type theory system, the type will be a fundamental object instead. So, for example, the real numbers are a type in Lean. A group is a type equipped with some other stuff. For example, a multiplication and an identity inverse, and satisfying certain axioms. And the key distinction I want to draw here is that in set theory, these would be sets instead. So to first order approximation, where you see a set in regular informal mathematics, in Lean, we're going to see a type. This is a first order approximation, but it'll be good enough for now. I can write down expressions. So I've got a few expressions here. There is 2, that's an expression. 17 plus 4, that's an expression. An expression is just something I can express. Now, each expression I write down has a type. And this command called #check is going to tell me what the type of an expression is. So I've got 4 expressions here. And in the blue next to the thing, Lean is telling me what the type of each of these expressions is. The first one is telling me that 2 has type natural numbers. And the way to intuit this is that 2 is a natural number. We then have that 17 plus 4 is a natural number. Then that pi is a real number, and that e is a real number. E looks a little bit different here. This is the real exponential function evaluated at 1. So this is really the number e that you're used to. Typically, if you hover over if you click on the underlines, on the right-hand side here, we get this nice view, which tells us the same information, that 2 is a natural number. If you additionally get this extension in VS Code, then it shows up nicely in line as well. I just want to use that for the purpose of demonstration so you can see all of these things simultaneously. Now, like I was saying, the way to read these things is as saying that 2 has type natural numbers. And it's really important at this point to mention that this relation, this colon relation, this has type relation, is definitely not symmetric. You shouldn't think of it as a ratio or anything like that. This is a type theory judgment. This is essentially an axiomatic thing we're starting off from now. Okay, so pi is a real number, 2 is a natural number. That's an expression, those are some types. But these types, they're themselves expressions. So this thing nat, it does have a type, and its type is type. Okay, so what does this mean? Just like we saw earlier that 2 colon nat meant that 2 is a natural number, this is telling me that natural numbers are a type, which should make sense. Similarly, the real numbers are a type. Okay, so types are expressions as well, just like our terms. For those who know, this is very related to Lean being a dependent type theory system. So I gave you some simple examples of expressions, but just dealing with 17 plus 4 is not particularly interesting. So here's another more interesting number, which is 7. On its own, that's not a particularly great number, but I've given it some meaning here. I've said it's my favorite number. So I've made my own expression, which is 7, and given it a name. I've defined my favorite number. I've said it's a natural number, the same relation as before, this colon n. And then we have this new part afterwards, colon equals 7. So this is defining my favorite number to be 7. And I'm also saying, look, it's a natural number. For any expression in Lean that I could give, there is a special placeholder called sorry. Sorry is basically saying, I'll do this later. I don't feel like doing it now. I'm just going to leave a placeholder and come back to this later. And to make sure I don't forget, Lean's given me this yellow bar saying, okay, warning, you've missed something out here. You need to come back to this later. And you can even see there's a warning symbol on the side. So we have a warning associated with sorries, but we can use this as a placeholder for stuff to do later. And the reason I've left this one as a sorry is that I know what my favorite number is, but I don't know what your favorite number is. So to fill this in, I need to know your favorite number. Can someone tell me a number?
42.
42, thank you very much. Now I know your favorite number, and the warning has disappeared. Excellent. And now that I have these two natural numbers, I can check their type, just like I did before. So my favorite number is a natural number, and your favorite number is a natural number. Excellent. So this is all well and good for writing simple natural numbers, but what we would like to do is do some mathematics. Or do some computer science or verification, but in either of these cases, we have something which we want to prove. And if I want to prove something, I need to be able to write down what I want to prove. And for that, we will talk about propositions. The type prop, this is a special type in Lean, and it contains all the propositions. Propositions are things which could be true. For example, 2 plus 2 is 4. Propositions could also be false, like 2 plus 2 equals 5. And some propositions can also be open. For example, is e plus pi an irrational number? So a proposition doesn't need to be true. It's just kind of a true or false question. It's something which could be true, could be false, but it's a true or false kind of statement. And when I'm writing a proposition like this, I can use any definition that was made earlier in the file or imported. And this isn't specific just for propositions. Any definition I write in Lean can use anything which was defined previously to that point. So as we're going through this file does have a linear order. As I go through the file, everything goes into the next part, and you can't go backwards. Okay, so we have these propositions, and Lean is telling me in each case, 2 plus 2 equals 4 is a proposition. E is less than pi is a proposition. 2 plus 2 equals 5 is a proposition. And then we have this open one. And I had this previous question, my favorite number equals your favorite number, which used to be an open question, but now thanks to Michael's help, it's no longer an open question, and it is now false. Just like I named my definitions earlier, I can also name my propositions. So here I've defined my very easy proposition. Just like before, I've said it is a proposition. And on the right-hand side, I've got this colon equals, and I'm saying this will be my proposition. So here we've got a couple of new bits of syntax. I've got this for all symbol and this exist symbol. But hopefully we can all figure out what this means. Lean's syntax is essentially designed to look the way it should look to a mathematician. Lean is very readable in this context. So I think we can all probably guess what this first one is saying. Can anyone tell me if my very easy proposition is, actually I wrote it down, but can anyone tell me why that one is true? People just have to have an answer. Why is the first one obviously true? Yep, exactly. So the claim is that for every natural number, there exists a larger natural number, and I can just use n to be that natural number, and it will work. The next one is a bit trickier. This time I'm saying that for every natural number, there exists a larger natural number p, which is prime, and such that p plus 2 is prime, and such that p plus 4 is prime. And this one is false, and you can see this by considering stuff mod 3. And the last one is an open problem. This is the twin prime conjecture, saying that there are infinite many pairs of primes. Okay, so now we've named some propositions, and now we're getting closer to being able to state interesting maths questions. But at some point, we will want to consider proofs. And so here is the key fact when thinking about mathematics in Lean. If P is a proposition, if P has type prop, like the 3 examples we just saw, any expression of type P corresponds to a proof of P. So here P is on the left, but if I have some expression where HP, for example, has type 2 plus 2 equals 4, then HP corresponds to a proof of 2 plus 2 equals 4. So if P is a proposition, for example, 2 plus 2 equals 4 is a proposition, then an expression which has that type is a proof of that proposition. I'm going to say that once more, just because it's so important. An expression which has a given type, which is a proposition, corresponds to a proof of that proposition. Okay. So let's see how to actually make these, because like I say, these things correspond to proofs and we want to care about proofs. So let's see how we can make these proofs in practice. The syntax to make these is just like we saw before, except instead of definition, we're going to write theorem, because we're going to prove a theorem instead of writing a definition. So here my theorem is 2 plus 2 equals 4. I've named it 2 plus 2 equals 4. And its statement is 2 plus 2 equals 4. But now I have got this right-hand side. I'm saying, what is the proof of this theorem? How am I defining what this what my inhabitant of this is? In this case, it's REFL. REFL corresponds to reflexivity. And so what's happening here is Lean is checking that 2 plus 2 is indeed equal to 4. And Lean is happy, and so I've got my nice blue ticks over here. Theorem feels a little bit much. All I've said is 2 plus 2 equals 4. I don't think anyone would fairly call that a theorem, so I could also call it a lemma as well. So I have the same thing, 2 plus 2 equals 4 again, and this time it's a lemma. The REFL refers to reflexivity of equality, and Lean is checking that both sides are actually the same, so this is true by reflexivity. So here are our first Lean proofs. They are simple, but they are proofs. Here's another proof, which is slightly less trivial. This time, I've claimed that 2 plus 2 is not equal to 5, and I've proved it using simp. I won't say too much right now about what simp is, and I'm going to come back to that later. Okay, so we have a proof, 2 proofs, relatively simple. And I've proved that 2 plus 2 is equal to 4, and that is not equal to 5. One thing I will do at this point is change this to be 2 plus 2 is not equal to 4. And this, as we know, is false, but Lean is telling us this as well. We have now a new color. We've got red. This is an error. We've got an error message showing up, and Lean is complaining that this proof did not work. What's important to note here is that Lean is saying your proof of this didn't work, or isn't finished, or isn't valid. Lean is not at this point telling me that the theorem is false. All it's saying is that I haven't successfully proved the theorem. Okay, let me change it back so we don't have any errors. So in the same way that Lean checked that 3 is a natural number, and then reported to us, yes, 3 is a natural number. In the same way, Lean is checking at each point in the file, in real time, that the proof, which is the stuff after the colon equals by, does indeed have its type as what I claimed it was. What that means is Lean is checking that the proof we provide does indeed make sense in proving the thing I wanted to be proving. And so, in this way, Lean is verifying that our proofs are correct. I'll come back to how we construct some of these proofs in detail later. But for now, the key part is that we can write down statements in Lean in this way, and Lean will check that our proof we give for it makes sense as a proof of that statement. So I'll talk about this one more time in this context. So Lean is checking that what I've put over here corresponds to a proof of this statement. And if I change the statement to be something else, then Lean will complain, no, you haven't actually proved this thing. So Lean is going to check the proof I've gave and make sure that it proves the thing I've claimed to prove. Okay, great. Just like we used sorry for our definitions to say this is a placeholder and I'll come back to it later, we can also use sorry for proofs. So this is an open problem. This is known as the Erder-Strauss conjecture. It's an open problem in number theory. It says that for every natural number, which is at least 2, there exist 3 more natural numbers, x, y, z, such that 4 times x, y, z is equal to n times s plus y plus x plus z plus y times z. This is sometimes presented in a different way, but it's equivalent for this discussion. Okay. And in this case, it's an open problem, so we don't know what the proof is. And so I've just put in this placeholder sorry, so that we can fill it in later once, hopefully, we find a proof. Maybe it's false. I think everyone thinks it's true. And it gives us a yellow warning just in the usual way. Okay, so we've seen some statements in increasing difficulty, but let's see some more involved ones to see that we can do some slightly more non-trivial mathematics. These ones are still relatively simple in the scope of what's been done in the context of Lean and MATLAB, but they're short enough for me to be able to explain them in a few sentences. Okay, so the first one, it's hopefully fairly readable to most people in this room. It's just the cosine addition rule. Cos of x plus y is equal to cos of x times cos y minus sine x times sine y. I've given the proof here, but let's not worry too much about the proof. Hide the proof even. And the statement reads fairly nicely. Like I say, Lean syntax is designed to look fairly similar to mathematical syntax that you're used to, with one distinction that I haven't put brackets around x inside the cos x. This is a thing which is typical of functional programming languages. It's something you eventually get used to with Lean, but that's a key difference to be aware of in that you typically don't write brackets around function arguments, but I will need to write brackets around this. So I do need to put brackets around the x plus y because this is grouping the x plus y together. If I didn't put those, then what does this mean? This means cos x plus y. So I'm taking cos x and adding it to y. Okay. So that's something to bear in mind, that some of these brackets might not be where you expect them, but over time you get used to it. Here's another example. This is an example from MATLAB. This is the theorem that if you have if the closed ball in a real vector space is compact, then your real vector space is finite dimensional. So let me talk through this one in a bit of detail. So K is my type. This is going to correspond to my base field. Typically, this will be reals or complexes. I said the theorem for reals. It's you look on Wikipedia, I think it's stated for reals. But the MATLAB version of this theorem works for any non-trivially normed field. So these first two things are saying I have K, which is a non-trivially normed field. Non-trivially normed field is something defined in MATLAB somewhere, and I hover, and Lean will tell me. A non-trivially normed field is a normed field in which there is an element of norm different from 0 and 1. This means it's possible to bring any element arbitrarily close to 0. Okay, so presumably I have a normed field, and the norm is not completely trivial. Okay. Then I have two more things. I have E, which is just another type. We're going to think of this as our space. And I have two assumptions here on E. The first one is saying that it's a normed additive commutative group, and the next one is saying that it's a normed space over K. So in combination, these three things are saying that E is a normed vector space over our base field K. If you don't know enough analysis for this to make sense, that's okay. All I mean to say is that in MATLAB, we have the tools possible to express all of these notions. Okay, the next one is completeness. So our underlying field must be complete in the usual sense of Cauchy sequences converge. Then I have R. R will be the radius of my ball. And I'm saying that my ball has positive radius. So it's not a trivial ball. And this is how I construct the ball. I construct it by saying the closed ball centered at C with radius R, and H is my hypothesis that that ball is compact. So I'm taking the closed ball centered at C of radius R and asserting in my assumptions that it is a compact set. There's something new in this example, which is that I have named this fact. I've said this ball is compact, but I haven't just said that it's compact. I've said it's compact, and I'm naming this fact H. That's what this left part is doing. It's naming this assumption. So in this example, I had x and y as real numbers, and I named them because that would make sense. But something that we do in Lean that you wouldn't typically do is name your hypotheses as well. So I've named the fact that my R is positive, and I've named the fact that my closed ball is compact. And then after the colon, just like before, we have the conclusion, which is that our space is finite dimensional. Okay, so here's an example of a slightly more complicated theorem using some more tools from MATLAB, which has some more interesting features to it. We have different type of brackets, which I won't say too much about right now, but these are just different types of assumptions. And we have named hypotheses, and it's mathematically a more interesting example. Okay, great. Finally, the last thing I should talk about in terms of definitions is we can also define inductive definitions. Here's an example of an inductive definition. I have defined my version of the factorial function. It's the usual one, but I couldn't name it factorial because it clashes with the one in MATLAB. So this is my factorial. And I've defined it in the usual way that you'd be used to. I've defined it at 0 to be 1. I'm going to define it at n plus 1 to be n plus 1 times whatever the value at the previous point was. So I can also express recursive and inductive definitions in Lean using this syntax. Other syntax is available, but I think this one looks nice. Okay, this is a good point to stop for questions. Any questions at this point? Please.
How do you import all the symbols that you are using? And also, how do you render the natural as n double bar instead of not?
Okay, so the answers to both of these is the same. In this case, I've done import MATLAB. So import MATLAB at the top of the file will import all of the definitions and notations from MATLAB. And in the particular case of your example, it's going to import the notation of the Unicode natural number symbol for the natural numbers so that I can use it, and also so it gets rendered like that. So for both parts of your question, the answer is the same, which is to put import MATLAB at the top of your file.
And OpenReal?
OpenReal is not necessary for the natural numbers, but that was necessary to talk about pi. So the pi notation and symbol, that works because I did OpenReal. You don't need to do that for the others.
Because I'm an example.
Yes, exactly. So if I didn't do OpenReal, then it's ambiguous if I mean the real cosine function or the complex cosine function. And so OpenReal tells Lean, okay, I care about the real one for now. Okay, great question. Any other questions? Yes.
Yeah, I have a question about there is a when we are proving the compactness.
Yes.
Can we see that slide? Defined. For example, we are writing exact and then writing some statements. Is it another theorem that it's already available in MATLAB?
Yes. So this is the name of the theorem from MATLAB, and I'm essentially saying use that theorem from MATLAB to prove this one.
Yes. And then we create another theorem, right? And then if that theorem is published through MATLAB, it's possible to publish this and then use it for other proofs, right?
Yes.
Okay.
So someone had proved this. They then pushed it to MATLAB, and then I downloaded a copy of MATLAB, and I can use that proof to do my proof. In this case, it's a trivial application, but someone could have done a non-trivial application as well.
Okay, thank you.
No worries. Everybody happy? Excellent. Okay, so we've seen some definitions, we've seen some very simple proofs, but let's talk more about these things. We're here to formalize mathematics, and a big part of that is proofs. So let's understand how these proofs work, what they look like in practice. The most common way to write proofs is using tactics. This isn't the only way, but it's the main way I'm going to talk about. It's the most common way in which you'll interact with proofs if you're doing maths in Lean. It's not the only way, but it's the way I'm going to talk about and focus on for now. Let's look at an example from real analysis. This example is taken from Patrick Masseau's Glimpse of Lean tutorial. To do so, I will start off with two definitions. The first definition is that of the limit of a sequence. So here I'm taking in two assumptions. I'm taking in two inputs. The first one is that I have a sequence U. The sequence here is represented as a function from the natural numbers to the real numbers. And if you think about it a little bit, that's what a sequence really is. For every natural number, I get a real number. That's a sequence. So u is my sequence, which is a function from the natural numbers to the real numbers. I then have another input, which is L. This is going to be my hypothetical limit of the sequence. And the property of this sequence having this limit is a proposition. It's a true or false question. And how is it defined? It's defined in the usual way that you're used to from real analysis class. It's that for every positive epsilon, there exists a capital N natural number, such that for all little n bigger than big N, the distance between un and my hypothetical limit is bounded by epsilon. Okay, so hopefully this is familiar to everyone as the usual definition of the limit of a sequence. Or to be more specific, this is the usual definition of what it means for the limit of the sequence u to be equal to L. And just like before, we don't have brackets. I haven't written u. I haven't written something like u bracket n. We're writing u space n. Okay, so this is the limit of a sequence. The next thing I want to define is continuity at a point. This time, I'm taking in a function, f, from the real numbers to the real numbers, and x naught will be my real number. And what I'm going to ask is, what does it mean for f to be continuous at that point x naught? And just like before, we're going to use our usual familiar real analysis definition, which is that for every positive epsilon, there exists a delta such that for all x which is close enough, then f of x is close enough to f of x naught. Okay, so here are our definitions. And like I was saying earlier, if you have some definitions earlier in your file, you can use those to state and prove a more interesting theorem using those definitions. This one is an example. Example means the same as theorem, it just doesn't have a name. So this is just another theorem. And what are we taking in? So before this first colon, I have all of my assumptions. After the colon, I have the thing which we are going to prove. And then colon equals by marks the beginning of the proof. So again, before this colon, I have all of my assumptions. After the colon, I have the thing I'm going to prove. And then I have the colon equals by, which marks the start of my proof. So let's go through these assumptions. I have f, which is a function from the real numbers to the real numbers. I have u, which is a sequence. And I have x naught, which is some specific real number. I'm then asserting that the limit of the sequence u is x naught. So this sequence u limits to x naught. And f is continuous at that point. And just like I was saying earlier, we name these assumptions. Why do we name these assumptions? It's because that makes it easier to refer to them in the proof. We name them so that when I want to use this fact during the course of my proof, it has a name. Now I can talk about this thing. Okay, so that's the assumptions we have. What's the thing we want to prove? What we want to prove is that the composition f of un is the way you might write it informally. In Lean, I'm going to write the composition of f with u. So this is a new sequence. I'm going to say the limit of the sequence will be f of x naught. That's the thing we're going to aim to prove. And let's now step through the proof. I won't step through the mathematical details of it so much. This file will be on the Italian GitHub, so you can see it and poke around with it yourself afterwards. But what I want to focus on instead is this tab on the right. It's been there the whole time, this thing on the right. But that's going to be really important when reading and writing Lean proofs. It hasn't really come up so much so far, but what we're going to see now is that that's a big player in the game. Okay. So what is it telling us right now? Is the laser pointer visible at the back? Nice. Okay. So I have my same 5 assumptions that I had earlier. Same 5 things I said that I'm going to assume in the context of my proof. And they're even in the same order. So I have f, I have u, I have x naught, I have hu, and I have hf. And Lean is telling me, yes, f is a function from the real numbers to the real numbers. U is a sequence. And just like before, we have all these things. And then I have this last one. This last one is distinguished from the others. It's got this turnstile symbol in front of it. This one is the one I need to prove. Everything above this is my assumptions. And this last one is the one I need to prove. And just like we wrote in our statement, I want to prove this limiting property. And so Lean is telling me, yes, well, okay, this is what you need to prove. What we then do is the lean user or whoever's writing your proof will write a sequence of lines. So this first one is an unfold, then there's an intros, then obtain, and there's a sequence of lines. As I step through these lines, watch what happens to the info view. So this right-hand side tab is called the info view. And as I step through these, that's going to change. That's changing as I go through the proof. Stuff's getting added. The stuff at the bottom is changing. It's changing repeatedly until suddenly it disappears. And it says no goals. Well, maybe you didn't notice what was in blue at the top before. What was in blue at the top before was one goal. So I went from having one goal to having no goals. Great. So what does this mean? At each point, Lean is telling me this is what you know, and this is what you need to prove. As I step through these lines, these tactics, the things I have and the things I need to prove are changing. In the first one, I originally had to prove that the limit of a sequence is something. And then after I do this unfold, Lean is going to unfold that definition, which I wrote earlier, and change this to a for all epsilon statement. This is a very low-level step, but it's a useful step because now I'm essentially recalling the definition. Then what's the next step in your proof? The proof, as any undergraduate would know, if you need to prove something for all positive epsilon, the first thing you say is always, let epsilon be positive. And in Lean, we write that using intros. So I say intros epsilon h epsilon. And let's take a very close look at what's changing here. First, I have a turnstile, and for all positive epsilon, something. After this line, my first 5 things are the same, but I've got 2 new ones at the bottom. I've even very helpfully got them highlighted in green, so you can't miss them. I have these 2 new things, epsilon and h epsilon. Epsilon is a real number, and I have asserted that it's positive, and I've even given a name to this, h epsilon. Okay, so in this intro step, I've got these 2 new things to work with. I have these 2 new assumptions, epsilon and h epsilon. But also, the thing I have to prove has changed. Originally, I had to prove something for every epsilon. Now I've got access to some epsilon. I've let these epsilon exist. And then now I need to prove something for these specific epsilons. So this corresponds to the usual proof step you would see in informal mathematics of let epsilon be positive. And that change is reflected in the info view that Lean is showing us. Lean is saying, well, now you've got these epsilon, now prove the thing using these epsilon and h epsilon. Okay, so what's the next step in our proof? The next step in our proof is going to be to use these epsilons in the definition of the limit of the function. So in our notion of what continuity meant, continuity of this function around this point, it was a epsilon delta definition. So I'm going to feed, let's not focus so much on the syntax so much. What I want to focus on is what's happening in the info view. I'm going to do this obtain line. And as I do this obtain line, we're going to end up with 3 new things. I've got delta. I've got that delta is positive, and I have some property about delta. If you inspect this property about delta, this is exactly the property you get from the definition of continuity at a point. I now have that for this epsilon, which intros or let gave us earlier, for every real, which is close enough according to delta, then the gap between f of x and f of x naught is at most epsilon. This is the usual definition of limit of continuity of a sequence, sorry. Okay, we'll do the same thing again with the limit, and we'll get access to this capital N. Now, I have to prove that there exists an N. But I've got access to some now. I've got this N, which is a natural number. Lean is very helpfully telling me N is a natural number. And so I want to say, this is the N I want to use. You ask me for some N, here is the N. And I will say, use N. Okay, well, now I need to prove for all. The way to prove a for all is to use intros. So as we go through these steps, our info view is changing. And our info view is changing in a way that corresponds very closely to the usual proof that you're familiar with. Until I get right to the end. What's this very last step? Well, the thing I need to prove is that un is sufficiently close to x naught. Un is sufficiently close to x naught. And I have that in this HU assumption. For all n which is big enough, un is indeed close enough to this x naught. And I know that I do have some n which is big enough. So I can apply that and finish the proof, and we have no more goals. Okay, so the takeaway from this is that we write our statements. We have a list of assumptions. we have the thing we want to prove, and then we have our proof. Our proof looks like a sequence of steps. In this case, they were very small steps. These are kind of almost atomic steps. And as we go through these steps, Lean is telling us, this is what you have, this is what you need to prove. And we go through these steps until we end up needing to prove a triviality, and then we are done. So a proof in Lean looks like a sequence of tactic steps, each one getting us closer to the goal we're looking for, until we get there and we have no more goals. Great. So like I say, tactics allow us to build up proofs step by step. And Lean gives us the tools to keep track of what we have so far and what we still need to prove. Now, I showed you a couple of tactics in that example. We saw unfold and intros and use and stuff like this. And so clearly it's going to be very important to know what some of these tactics are. And so this cheat sheet, which I in fact already had open, this is a 3-page document with the essentially almost all of the key tactics which you will come across. And so it's a long list. I will go through some of these later, but I would encourage you at some point. I will post this link on the GitHub and everything like this. I would recommend, if you are not already familiar with Lean, to have this open on your laptop at all times. It's going to be incredibly useful. If you are stuck, consult this sheet. And I'm going to go through some of the most important examples so you can get an idea of what using some of them is like. But there are lots of tactics to do lots of different proof steps and proof ideas. And in order to get where you're going, knowing which steps you have to get there is going to be incredibly vital. Cool. And like I said, I will go through a few examples. I won't go through all of them. Like you saw, it was a long sheet. But I'm going to go through a few of these examples so you can see what they look like. I'm in particular going to group them into 3 categories. This categorization isn't an official thing. This is something which, it's a conceptual thing which I like to think about in this way. And the idea of this categorization is it's roughly according to the power or difficulty or conceptual stuff going on in each tactic. So we're going to start off with the simplest ones. I call these the level 1 tactics. I'm going to show you a simple proof using these most basic tactics. And these are essentially good for very basic logical things. This is the sort of thing where you wouldn't usually write this down in an informal proof, but it's useful to be able to express these in Lean. And so these are the most low-powered, essentially, tactics, relative at least to the ones we're going to talk about later. And so what that means is they will do very specific, very targeted things. Here are a few of them, and then here is an example with them. Let's talk about this example. What do I have in my context? I have P and Q are propositions. Like these are true-false statements. These are things which may be true or they may be false. And I'm going to attempt to prove that if I have 2 of these true-false statements, P and Q, then P and Q implies P or Q. This might at this point be feeling like your first or second year undergrad logic class or something fairly tedious like this. And that's fair. This is a relatively simple exercise. This proof is quite a long proof, and in the actual practice of using Lean, no one would really write a proof like this. But I'm going through this to show you these kind of low-level tactics so you can see what's changing in the info view and how these proofs can look in practice. Okay, so what do I need to prove? I need to prove that P and Q implies P or Q. And the first thing I will do to do this is use the intro tactic. The intro tactic we saw earlier to go from a for all into a let kind of thing. The intro tactic also does implications. So here I need to prove that P and Q implies P or Q. And the intro is going to make this very useful transformation of naming this assumption and taking it up into my assumptions. So now I know that P and Q, and I need to prove that P or Q. Well, I know that P and Q, so I should know P and I should know Q. So how do I get access to these? I can use the obtain tactic. The obtain tactic will break down this conjunction, it will break down this and into 2 separate things, and it's going to name them H1 and H2. It's named them because I typed in here H1 and H2. So after this obtain, I have H1 is a proof of P, and H2 is a proof of Q. And well, the same thing I need to prove. I haven't changed that point yet. All I've changed is my assumptions. What do I need to prove now? I need to prove P or Q. Well, I know that P and I know that Q. So I've got plenty of choices. I could either try to prove the left disjunct or I could try to prove the right disjunct. I pick the left one. The left one is P. So when I say I want to prove the left one, Lean says, okay, now you have to prove the left one. The left one is P. So I need to give a proof of P. And finally, I use the exact tactic. The exact tactic is useful for exact matches. So I need to prove P. Well, I already have this thing, which is a proof of P, which is H1. H1 here, Lean is telling me this is a proof of P. And so I say, well, use exactly H1. I say exact H1, and then we finish our proof. We see a message, goals accomplished, and then no more goals. Okay, so these are the kind of very basic logical steps. One other thing which is kind of in this category are have and suffices. Have and suffices are very useful tactics to express intermediate steps. So here I have P, Q, and R are propositions. I know that P implies Q, and I know that Q implies R. And finally, I know that P is true. What do I want to prove? Remember, that's after the colon. I want to prove that R is true. The colon equals by starts my proof. And the way I want to structure this proof is saying, well, okay, in this context, I know that Q is true. So let me first prove that Q is true and give it a name. The name will be HQ. And in order to do this, I need to actually prove that this is true. So I'm now starting a new sub-proof block. This is, a sub-lemma. It's a have block inside my thing. And just like before, colon equals by is going to start my proof. So I've essentially paused my main proof because I'm going to prove this sub thing in the same context. And then after I finish doing that, so let's put our cursor here to see what happens after I finish doing that. Actually, in particular, let's compare. So before I had HP as a proof of P, and I had to prove R. But after this have block, I've got this new thing that's appeared. Now I know also that Q is true, and that it has a name, which is HQ. And then I can use apply to apply this implication, and then match it with HQ to finish off. So this have tactic is very useful to express intermediate steps in a proof. The suffices tactic does the same thing, just kind of in the opposite direction. Instead of saying, well, first I'll prove Q and then I'll keep going, you could say, well, it would suffice to prove Q, and then I'll come back later and prove Q. The reason I want to emphasize these two particular tactics, have and suffices, is that during the course of the week, I imagine a good chunk of us will be using Aristotle to find proofs. Aristotle likes this style quite a bit. Aristotle likes to do have statements in the process of getting to a proof. And so these are often quite nice if you want to understand what the proof is doing. You can look at the have statements and they will give you a reasonable clue as to how this thing was broken down. So have and suffices are indicators that a proof has been broken down in this particular way. Okay, here's one more tactic, the rewrite tactic. It's also somewhat straightforward. It's useful for writing along equivalent propositions. So I have P, Q, and R as my propositions. P is equivalent to Q, so P if and only if Q. I've got this nice symbol for if and only if here. I have Q or R. Again, I have nice Unicode symbols as usual. And I want to prove that's P or R as well. And I can use rewrite to say, well, okay, I know P is equivalent to Q. So anytime I say P, I can turn it into a Q because these two things are equivalent. I will use the rewrite tactic for this. And we can see that the P has turned into a Q. And then we have an exact match with H2. So we finish our proof. No more goals. Now, rewrite is not just for if and only ifs. It's also useful for equalities. And in fact, that's kind of the more common case, and that's what it's really built out of anyway. So really, this is the key one, not the earlier example. The rewrite tactic can be used to kind of chain equalities and prove equal statements in this way. So let's go through this example. I know that A times B is equal to C times D. I know that E equals F. I need to prove that A times B times E is equal to C times D times F. And I can do this with a sequence of rewrites. Each one is going to change what's happening. You can see this red highlight. This red highlight is indicating to me what is about to change. And as I move my cursor through, you can see my cursor on the left is moving through the statements. We've seen the red E turn into a green F because I've rewritten along H prime and I have the new thing to prove, which involves F. Then my next example, I'm going to use this lemma from MATLib, which is the associativity of multiplication. And as I do this, we can see again the red turning into the green, and the brackets have moved because this corresponds to an associativity claim. then I will do the same thing. I will rewrite with h, and then use one more associativity step. Now my two things are equal, and Lean is happy to say, yeah, okay, now you finish your proof, no more goals. Excellent. Okay, here is one more example. Here I want to prove that a plus b times a plus b is equal to the usual expansion that you'd expect it to be equal to. And I've written a sequence of rewrites to get you there. You can use essentially the axioms of ring in order to get you to what we need to prove. But this is pretty tedious. I'm not even going to bother to go through this example. No one in practice uses the axioms of a ring. And so we move on to the level 2 tactics. The level 2 tactics will have more automation. So far, we've done very manual steps, but more powerful tactics will do more interesting things. They will kind of combine and condense some of our earlier steps to get to more interesting parts. So here is the ring tactic. And instead of the tedious sequence of rewrites which I had before, I can just write ring, and ring proves the thing. So here, I had to write this long sequence for Lean to be happy, but in fact, I can use this more powerful tactic, ring. There is another powerful tactic of this flavor called simp. The simp tactic is Lean's simplifier. There are a bunch of lemmas throughout MATLAB which people have tagged simp. The tag means this is a simplification lemma, which means anytime you see the left-hand side, it is simpler to turn it into the right-hand side. And so when I use the simp tactic, Lean is essentially going to go through the library and find everything of this form which matches what I have to prove, and turn every instance of what I find on the left into what is meant to be on the right. So in this case, my statement here is that, so fin n is the type of natural numbers less than n. So essentially the set of things which are less than n. And I'm saying well, the cardinality of the set is indeed n, because we include 0. Now, maybe I don't remember the name of this theorem. It'll be in MATLAB somewhere. But simp will just go and find it for me, and simp will prove this lemma for me. And what's important in this case is that simp will only use the lemmas in the library from left to right. So it's only do simplification steps. Okay. Here are some more examples. I won't go through these in too much detail. These are on the same cheat sheet. But in each of these cases, you kind of automate some of these less interesting parts. So in this case, I've proved that the function sending x to x plus 1 is a measurable function, or that x times sine x is a differentiable function. The fun prop tactic is very useful for proving this kind of statement. And for the examples I showed, there are other tactics which would work. So here are examples of the cutsat tactic working, which has now been renamed, but in the version of Lean we're on, it was cutsat. And here's another example using the Grosvenor tactic. There's also the linearith tactic. And n-linearith comes up every now and then. Again, large language models like to use n-linearith. Okay, so those were our level 2 tactics. We have a bit more automation. We've hidden away some of the more tedious, boring details. And then we move to our level 3 tactics. These ones will be more automatic, sometimes slower, sometimes faster, in general slower though, but that's because they're doing much more. These tactics are significantly more powerful than the ones in level 1, and they will be able to prove more difficult things automatically. The two I've highlighted here are ESOP and grind. A very basic explanation of the ESOP tactic is it does search in tactic space. So it's going to attempt to find sequences of tactics, like I wrote earlier. It's going to attempt to find sequences of tactics which will prove my goal. For example, if a proof is some combination of the intro and simp and x tactic, which I didn't talk about, but it's another tactic which can be used, there's a good chance that ESOP will find the proof. It's going to kind of search through what are the different things you could have written down as a tree search, essentially, and try to find the proof which works. The grind tactic also does search, but in a very different paradigm. There is very nice documentation on grind, which explains this very clearly. All I will say is I'll just give a very simple example of grind working. This is one of the many things it can do. I have a function from the real numbers to the real numbers, and I said that f of x equals x, and the fivefold application of f to x is also equal to x. And in this context, grind has figured out that, oh, actually f of x must be equal to x. The way you can picture this proof intuitively is that with these two assumptions, you can kind of plug them into each other. If I apply this guy inside this one, then it's going to make a change. And you do this enough times, you're able to prove this. And Grind has kind of written out all this calculation on its internal whiteboard and found a proof of this thing and sent it to Lean, and Lean was happy with the proof. This is not the only thing Grind can do. In fact, the two examples I gave here of Grosvenor and Cutsat, these are also modules of Grind. These are kind of special cases of Grind. So Grind is an incredibly powerful new piece of automation we have. But there is one thing which both of these struggle to do in the general case, which is fill in existential statements. If you need to prove that there exists n with some property, in general, Grind and ESOP and most of the inbuilt Lean automation we have will struggle to prove this kind of thing. And this is where AIs come in. So, in summary, proofs are constructed by sequences of tactics. These tactics can vary quite heavily in terms of their scope, what they're meant to do, their power, how useful they are in practice, how readable they are, and their speed, kind of the speed of execution, and also speed of typing. This PDF document of cheat sheet is very useful. Again, I'll send a link. And an AI system designed to use Lean will find tactic proofs, writing usually line by line, using tactics from all of the three categories I mentioned. It's going to use a combination of all of these, and so you will see many of the tactics I've talked about coming up in practice. Okay, I think I'm out of time at this point, so I will leave it there and take any questions. Thank you.
Okay, so we have time for maybe 2 questions. So please. Yeah.
I don't think my explanations were that clear.
Oh, one here.
So suppose I want to prove a theorem which is already in MathLib,
Which is what was
already in the library.
Yep. Okay.
How can I know this?
Great question. There are lots of different ways to know this. The easiest one to demonstrate, in fact, I have an example from earlier. When I had this Reese theorem, let's see if I can find it. Here. So I have this thing in MATLAB, and there is some exact match in MATLAB, which is why I used exact. And if I want to find this, then I can use exact question mark. Exact question mark will search through MATLAB and try to find something which exactly matches. And right now it is doing search of MATLAB, and my laptop's kind of slow, so it'll take a little bit of time. But it eventually will say, well, this is the exact match, and then it will let me replace this with my proof. Okay, so this is the kind of inbuilt Lean way, as it were. I can write exact question mark, and Lean will perform a search to find inside MATLAB the thing I'm looking for. Okay. Another thing you can do is all of MATLAB has documentation. So you can see in the documentation, you can search the documentation, or you can even go on Google and say, I want to search the documentation, and type in the things which are relevant for your theorem and hope that it comes up. There is another tool. Oh, there we are. We've got the example from exact question mark. Okay. There's another tool called Lugal, whose creator is also in this room, as is many of the things I've talked about. With Lugal, if I give the individual components of the thing, so maybe I will state, well, the closed ball is compact and I want to prove finite dimensional, then Lugal will search through MATLAB and see things which match those patterns and return me all theorems which mention those two concepts. So that's kind of a syntactic search. And then there are also AI-based tools. So for example, there is Lean Search. So if I type in Lean Search, I want Reese theorem. So Lean Search, because it's a large language model-based system, I can type a question in natural language, and it gives me the Reese extension theorem, which is not the one I wanted, but I guess I was a bit ambiguous. And then it gives me different variants of Reese's theorem. In this case, it first tells me that locally compact norm vector spaces are finite dimensional, and I have the statement here. And hopefully if I scroll enough, then I get the same example I showed, which I think is this one. So we have a bunch of different tools for searching for things in the library, depending on the way in which you want to search. Maybe you want to search in natural language, maybe you have a Lean statement and you want it to be an exact match, or maybe you have some components, or you can look in the relevant library. So there's the kind of the four ways in which you can search things in MATLAB.
Okay, so another question. Yeah.
Hey, thanks for the nice talk. I had one question regarding, so when mathematicians, they are formalizing MATLAB,
Yep.
how much they care about readability of the proofs. So, I mean, when I'm saying readability, of course, static style proofs, they are readable, as you mentioned, but they hide important details. For example, you're using simp, grind, but we don't know what's happening underneath. So is there a concern, or it's just like, okay, we don't care, we are able to prove them and Lean is verifying it, so it's okay.
So this is a great question. I think there is no kind of community consensus, and at the moment it's to some extent down to what the author wants. But that said, maintainability of MATLAB is fairly important. Lean, one of the amazing things about Lean is that it changes and grows so rapidly. What this means is that MATLAB is built on top of Lean, so MATLAB needs to adapt to Lean. And so it's fairly important that a proof in MATLAB is, when Lean changes under its feet, essentially, that the proof can stay continuing to work in different versions of Lean. So readability and understandability of the proof is very important from a maintenance point of view.
But right now, is that happening? Are there guidelines for writing proofs, or how one should write proofs? Because there are guidelines about PRs and like how one should push things to the MATLAB.
Yep.
But when we talk about writing proofs, is there a particular style that mathematicians has to follow?
There are a few conventions that we follow in MATLAB. For example, not using simp in particular ways. I would argue that it's generally pretty lax, that in general, you're pretty flexible to do as you like, as long as you follow this short list of conventions. But there is a list of things you can do. If you go on like the MATLAB, I think, contribution guidelines, you can read about these.
All right. Thank you very much.